In that time, I was a PhD student, so I was the youngest among the participants. Now, I'm the oldest. Okay. One of I'm sorry, one of the oldest. Okay. Today I will speak about a result joined with Wen Huang and Song Shao. So this is the plan. So after introduction, we will introduce 3 tools we needed to prove this theorem. Then we give the proof. So it's clear there are the following levels of bigness, the subsets of S, N or Z. So the first one is synthetic or piecewise synthetic. Another one is positive upper density or positive upper Banach density. The third one is like this. Sum will be equal to infinity. So basically, one use topological dynamics, ergodic theory for Fourier analysis of higher order to deal with them respectively. Okay, in today's talk, I will show how to using the topological method to prove the following theory. Say, if Pi be integral polynomials vanish at 0, if F is piecewise synthetic in Z, then the pairs satisfy these conditions is piecewise synthetic in Z square. So the general ideas of proof. First, we transfer the question into the dynamic ones. Then we use the Nilpotent structure. This is known before. And also we should prove some, we call the saturation theorem for polynomials to solve them. So let me recall what is piecewise synthetic. So if F is synthetic, it means in a ball fixed diameter, you can find a point in F. It's piecewise synthetic. It means you have a synthetic that F1, you have intervals, the length goes to infinity. So this is the intersection of F1 of the union of these intervals. So it's the same for Z2. So you find at least one point in a fixed both on both of fixed diameter. So if piecewise synthetic, if you have intervals like this, I, N, J, N, both of them, the length of both of them goes to infinity, and F is the intersection of this one. So this set sometimes is called the 6 set. So piecewise synthetic set is the synthetic intersection of a synthetic set with a 6 set. So this solution can be extended to any group. Okay, the set of piecewise synthetic set will be denoted by FPS, piecewise synthetic. So syntheticity appears very naturally in the study of dynamic systems. So we say a dynamic system is minimal if the orbit of each point is less in X. So if it's minimal, if you pick X and its neighborhood, then we'll call this return times is a synthetic. So using the first corresponding principle, a piecewise synthetic subset is related to a minimal system. So you just consider the indication function in the shift in the symbolic system. We want to remark. So this result was proved by Furstenberg and Glasner when all the polynomials are linear. Later, it's Borg, okay, he provide a very simple proof. Then you see this result by Vidali and Liebman showed that if F is piecewise synthetic, then this set is infinite. So also our result is one of the questions asked by Będlewo and Hinman in some paper. This is one of the motivation in some sense. I will show you another motivation. So this is the combinatorical version. The dynamical version is the following. You have a minimal system. Then for each X and each neighborhood of U, this pair satisfies this condition is piecewise synthetic. Okay, later I will give another version of our result, which is convenient proof using dynamical method. So another motivation is the following. In some survey paper, Furstenberg wrote, in every topological dynamic system, you can find a point which is multiple recurrent. He wrote, on the other hand, we do not know if there always exists a point which is multiple minimum. In some paper, we disproved, we give an example which has no multiple minimum point. So the difficulty of the problem is, if you want to answer the question, you should know exactly the written time where U is an open neighborhood of X. So the example we find is a minimal weakly mixing system. In this system has no multiple minimum point. So in fact, this system, for this system, each point XX is a recurrent but not minimum. So after giving the example, we start to think if there are any positive information on the question. So we found if XT is a minimal system, you see, for every open set U, you can find the X such that this set is piecewise synthetic. So we didn't see for each X and each neighborhood of U. Why? We conjecture that this result is sharp. In a sense, one cannot show there is a dense G data set such that for each X in X0 and each neighborhood of U of X, this holds. Why? Since we proved in the same paper, if for a minimal PI system, I will explain later, this property, I said here, is equivalent to the existence of multiple minimum points. But we think there should be a counterexample in PI system. So what is a PI system? So if you take a proximal extension, then this system should be the inverse limit of proximal and equicoordinate extension. So this is an open question. For PI system, could you find an example in PI system? Okay, then we try to see if it's true also for polynomial. So this is the question. If we minimal system, you have U and a non-empty open set. Is it true for you can find that some X in U such that this set is piecewise synthetic? So the question also has an affirmative answer. We proved in the same paper. And also it has a combinatoric counterpart, but not so nice. So I didn't state here. But this stimulated us to consider the double case for M and N. So then we found, no, this has been studied before. Okay, Yes. Yes. I said that. Yeah, I mentioned here is okay. Assume. So in the previous, yesterday, you know that. So give a nice talk on how to show the structure related to the Brownian systems. Now, in some sense, this talk is the application of the result. If we have a problem for minimal system, of course, first you should have a structure theorem to say there is a factor. Then you can, if you can show, you can reduce the problem from X to Z. Then you can also solve the problem in Z. Then you solve the original problem. So it's very important to find a suitable factor. So it cannot too large or too small. So it turns out the Brownian system is a good candidate in certain situations. So the existence has been proved by Hauskramas and Ye and Glasner, Ye. So the second step, we need to understand this pi. Oh, sorry. This pi from X to Z very well. So we will do it by proving saturation theorems for polynomials. Okay, for the third step, you see the Brownian system has a very nice algebraic structure. So you can do some calculation, so you can solve it. Let's go to, I will go this section very quickly since Jonathan has given the details of the construction. Okay, the system will assume X is a compact metric space. But even X is compact metric, even in this case, you will see at the end, we are forced to consider compact Hausdorff spaces. So for the D action, we use this to denote the generators. Okay. So this is everyone knows, I will skip. So here, what we, something new is an infinity step Brownian system. We see this is an inverse limit of near systems. Here, a K-stop Brownian system is the inverse limit of a K-stop near system. We don't emphasize the nilpotence here. Okay, let me recall what is the system is equicontinuous. So if 2 points are close, so the action from Gx, Gy, it should be close. This is the equicontinuous. So the regionally proximal relation, so for every U and V, a neighborhood of XY, you can find X prime, Y prime, and the G in G such that the distance is small. So this is a closely invariant relation. So it's very important to know when it is an equivalence condition. So this is done in the 60s, 70s. So we know at least when G is amenable, this is an equivalence condition. Okay, I think in the previous talk, Jonathan introduced for G action. For Z action, it seems simpler. So this definition given by Hauskramas, we say XY is the regional proximal relation of the D. So it means as before, but here you should find a vector in ZD such that for any epsilon in a cube, this condition should be satisfied. So for D equal to 1, this is nothing but the regional proximal relation. See, this means for D equal to 1, you need one condition. For D equal to 2, you need 3 conditions. N1, 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 N2, N1 plus N1. For D equal to 3, so you need find N1, N2, N3. So it satisfies 7 conditions. So this is N1 plus N2, N3, N1 plus N3, N1 plus N3, N2 plus N3, N1 plus N2 plus N3. Okay. So by the result from Hosmer-Mass and Ye, we know that this is an equivalent relation. Also, it can be lifted. I mean, if you have a factor map, you have a pair below. You can find a pair in the above. It can be projected down. Also, the deeper result is this X infinity is an inverse limit of linear system. So if you let regional proximal infinity is intersection, then you will see this is the infinity step for linear system, of course. So this result proved by Hosmer-Mass using the ergodic method. So it can be proved by other methods. I mean, from the organizers of this conference and the co-authors. This is the first talk. I'll go very fast. The second talk we need is the so-called saturation theory. So in ergodic theory, if you want to know the L2 convergence of multiple ergodic averages, so the result by Hosmer and Nicola, you know that it can be controlled by the expectation of F to the Z minus 1 factor of the Pronyl factor. So I think people for a long time to think that there should be some version, the topological version of this theorem in topological dynamic systems. So you will see, but unlike the situation in ergodic theory, here we need a modification, so such that the resulting factor map is open. So there's some additional things you should consider. Okay, so this is the form we formulate like this. Let xt be minimal and pi from x to x infinity. This is the infinity step Pronyl factor. So this is a factor, but the pi is not necessarily open. So we need some modification. This is called almost one-to-one modification. This means the point, the preimage is a singleton, is a dense jitter set. Then you will find this pi, the resulting pi star will be very nice. So this is a D-step topological characteristic factor of X star. Okay, I will explain what does it mean, why we call this saturation theory. We now explain the notions. So if you have a pi from X to Y, a subset A from X is called pi saturated. You see, if pi is the inverse pi A is A. So it means if A touches some point in a fiber, the whole fiber will be in this set. So now we let tau D is T cross T square cross TD. If you have a factor map, we say XT is a D-step topological factor. So if you can find a dense jitter set of X, for each X from the omega, so you consider the orbital closure. So this is a subset of XD. This LX is pi cross plus pi saturated. So it means if you have a orbit here, so if you see the X star, so the fibers will be occupied. So it's more or less like the weakly mixing, but it's not weakly mixing. It's weaker than weakly mixing, but still is, in some sense, is complicated. So this is for linear. Also, a result proved by the Chu is for it's a little bit weaker condition, is weaker form. So now we have distinct non-constant integral polynomials values at 0. So it's the same. We have the factor, we have the modification, we get the pi side open. But here he said, if you have open set V0, V0, V1, V2 in the fiber, in the same fiber, then you can find some X in V0 such that this TP1NX in V1 and TPDNX in VD. Why we call this a weak form? Since he didn't say for there is a density data set, it has this property. So, but this result is enough to solve the density problem. I mean, there's a very nice result by Likos and Berner, said if a system, ergodic system is totally ergodic, and then for any rational independent polynomials, the times average will go to the space average for the product. So this is the same. He solved the problem is if xt is totally minimal, then the orbit of this polynomial will be density xt. In some sense, it's a topological analog of the result. Okay, in our paper, we using some argument, we can strengthen a little bit. So we can find a density data set such that for each x in omega and the d, also this open set 1, U1 and UD. So this hold. I have a remark. You see, we state the linear theorem in a different form. Also, it can be stated in another form, like the polynomial case. So the proof of the Saturnian theorem, so it is given by 3 papers, is very long. So I will not discuss it here. So, but roughly speaking, you can think that so each minimal system is built by 2 parts. You have the structured part is infinity step polynomial system, and the random part is in above. So you have the saturation. You will see the almost one-to-one modification is necessary. Otherwise, you have a counterexample. This is a paper by Wu, Xu, and myself. Okay, this I have stated totals. The final total we need is the associated system related to a given topological dynamics and the finite collection of integral polynomials. So this is, we should pass our system to a very large system. So first, you see, for the linear case, Glasner introduced to the associated system ND. So you have 2, if you have 2 transformations, tau d and TD, then you form the orbital closure. So this is the group generated by TD and tau d. So when xt is minimal, this is independent of the choice of x. So you just orbit some x, you just choose some x. So a very nice result, also, as my understanding, it's also very deep, is if xt is minimal, then you can show nd and this group action is also minimal. So up till now, one can only prove it by Alice semi-group. So it will be very nice. You can find some elementary proof of this factor. Now, let me see if xt is a topological dynamic system. We have a very simple case. We have one polynomial is n squared. So we can define a system from xz like this. Here we have two transformations. One is T infinity is the product. Another one is the sigma, is the shift. So this is the simplest case, the associated system. The general case, we will have a subset from xd to z. So this point will be denoted like this form. So you have the shift. So this shift is not only shift only one coordinate. This is the d coordinate together. Then for each x, you can associate from to a and x. You have a sequence like this. This is a sequence from x to z. Then you defined like if the linear case is similar, you have two transformations, you get the orbit closure. Okay. It's not so difficult to say this is invariant under the action of T infinity and sigma. Also, they are community. So this means this is a Z2 dynamic system. Also, if xt is transitive, so the choice of x is not only depends on the transitive, do not depend on the transitive point. Okay, so if it's minimal, you can define the use of 1 point. Let me see some example. If A is just the linear polynomial n, you see this is just xt. If A is a collection of linear polynomials, then you will see this is more or less similar to what Annie defined. So in this case, this dynamic system is the minimal by the result of Annie. So when xt is weakly mixing, for example, if A is n squared, you will see this system is xz sigma. So from this, you will see that this system is not minimal in the above case already. So in the linear case, it's minimal, but it's for a polynomial of degree larger than or equal to 1, or larger than or equal to 2. It's not minimal. Since the diagonal is, how to say, is invariant, closed, and T infinity and sigma. So if A is n squared, then you have this. So if x is infinity step, then you can see, so is this system. Also, you will see if xt is distal, this system may not be distal. So the reason is above the infinity polynomial system, the map is saturated. That means like Brody shift, looks like the Brody shift. So you can pick 2 points they have a different coordinate at 0, but they can be the same at other coordinates. Okay. I promised another dynamical version. This is one. So the dynamic version we stated previously is equivalent to this one. So we should prove this system is an M system. It means it's transitive and the minimal points are dense there. So you cannot prove minimality. We will have example. So what the best thing you can expect, you can prove the minimal points will be dense. So this is what we try to prove. Another thing you should consider is, you see, in the saturation theorem, we need the polynomials are distinct. But if you're giving a polynomial, when you apply the saturation theorem, you will see sometimes this happen. So this is defined in this way. So we should exclude this situation. But it's fortunately, in any family, you can find a maximum family satisfies this condition. Okay? I mean, given a polynomial, finite collection of polynomials. For example, you have a n squared plus 2m. So if you apply this operator, so most of them are same. So you should exclude one polynomial from the family. Someone left. So you have the maximum family, you should be okay for us. Okay? Okay. So it's left to show for any family, this system is an M system. So we start from a simple case to explain you the idea. The simple case is minimal distal system. So you have only one polynomial with degree larger than or equal to 2. So this is the group we are using. We assume this pi is an equivalent extension. We assume this phi z to x infinity is a group extension. So we know every equivalent extension is a factor of a group extension for distal systems. But we don't know if the maximal infinity step Polynomial factor of z is also x infinity. We don't know. But we can just to explain the proof, assume. I don't know, maybe Thomas knows. So if you have a group extension, can you still have this x infinity is still the maximal infinity polynomial factor? I don't know, but we can assume. So I mean, if pi itself is a group extension, that will be okay, no problem. Okay, so this assumption is there's no danger. Okay, then you have the following. You go to the associated system. Now we have explained this is again an infinity step polynomial system. Then you know what's the better things is, the nice things you know. This pre-image is the product by the saturation theory. This is very important for us. So now we want to prove the minimal points are dense here. It's enough to prove the minimal points is dense here. So it's a factor. Okay, now you take a point here. You take arbitrary x from the fiber. Since this is minimal. We have proved for the infinite step Fourier systems, the induced system is still near system. So you can find a minimal point in a fiber. Now you can pick in the automorphic group Z such that Xi is phi Xi prime. So you form a transformation phi K like this, the periodic one. Okay. Then you will see phi Kx prime will, it has such a kind of form, will approach X. It's not difficult to show that this phi Kx prime is still here, also is G minimal. So this shows the G minimal points in the dense. So this is for the distal case. But for the general case, the idea is the same, but the proof is very much involved. Let me see why. So the ideas of proof of general case is similar, as I said before. So here you should consider automorphic group. Also, you need this elements here is mapping every fiber pi into itself. We need this subgroup. We need some notion called okay, I'm sorry, called the regularizer. This is a definition. So if you have an extension, see this is regular. If you have in a fiber to X in the same fiber, you can find some elements in this group such that these elements send X1 to X2. Fortunately, there's a theorem says that for every factor map, you can have an extension, okay, such that this phi star is regular. So you can make some modification to the factor map such that it is regular. Also, we need another notion is called RIC. It's relatively incontractable. So here you should some very little knowledge from Alice semi-group. So you see you have the minimal idempotent from UX is X. So this is the universal minimal set, minimal system. So you have this equality. So this is called a circle operator. It means you take this m lambda d lambda, you take the limit. And of course, this is the limit is not the, since here the space is already compact Hausdorff. You can only speak about net. So anyway, I don't want to bother you. You just want, okay, for you, every distal tension is IC and every IC tension is open. Okay, the final things we also need is also, you have some modification. If you have a factor map, then you can find some modification by proximal. This is the proximal extension, such that the resulting factor map pi prime is IC. Okay, this is so I can still have 5 minutes, right? Mm-hmm. So the first step, we construct this extension. Then we transfer this question to some extension. Then we choose a set of minimum points is dense in some certain region. So this is if the IC extension is a distal, this step has finished. You stop here. But the real trouble is if it's here is proximal, it's okay. The real trouble is when the extension is weakly mixing. In the weakly mixing extension, you have proximal part and then distal part. So you should do by 2 steps. First, you choose a set of minimum points dense in some certain region. Then you using the IC property to split the point, the whole space, okay? Okay, let me state some questions. So you have the piecewise density in F. You have the piecewise density here. So maybe I think there's some relationship between this one. Maybe I think the piecewise density here is dependent by the degree of the polynomials and also the piecewise density of the first one. This is, I don't know how to do this. The second one is how to generalize this to the commuting case. So you understand this method doesn't work. For the commuting case, the near factor cannot control the limit behavior. So here, maybe it's, I think you can find the combinatoric proof. So the first summary theorem, first you have a combinatorial proof, then you have a dynamic one. Now we have a dynamic proof. I want a combinatoric proof. If you have this, I think you can generalize to the, even for the Nilpotent group action. Yeah, okay. Okay, the final is a very general question. So we just do it, the saturation theorem for polynomial. So how to do it, say, for the set of primes, maybe Hadfield as Nichols does. Okay, thank you very much. Merci. No, we only have this example from horocycle flows. So the reason is in that class, people did a lot of investigation. So you can calculate it very carefully. So for the other class, we don't know. Also for the PI system, I'm very interested. So if one can find the example in the PI system, yeah. I guess it should be exist. Yeah. Pardon? I'm sorry. No, I didn't catch your question. I'm sorry. Ah, okay. I don't know. Just feeling. Why it should be there is such a point? I don't believe. So it's a very good question. I don't know. Maybe I think maybe yeah. For the hard field, you can do something. Oh, okay. Okay. How to erase this condition? I should think. Yeah. Okay. Thank you. Okay. Thank you for the remark. Yeah, okay. Thank you.